presentation because I was really notified on short notice to do this, and I decided to take this paper, which was not asked by Evgeny or proposed by Evgeny, because this paper actually came in February this year, but it is really interesting. I like it very much. It expands your horizons. I'll show you how it does this. So the main idea of the paper is take a dynamic problem, take a dynamic programming problem, cast it, like in C, into another type of problem, linear one, then relax the linear problem, and perform steps back, recasting this linear relaxed problem into dynamic problem. This relaxation enables, it turns out this relaxation enables incorporation of this approximation of the original dynamic problem into neural networks, and actually gives you an opportunity to work with structured losses, dynamic time warps, and sequence prediction. So here's the main idea of that paper. In a typical setting of dynamic programming, you have a direct acyclic graph. For example, alignments between a string, or, for example, if we're talking about looking for the optimal paths in this Floyd-Warshall algorithm, you have a graph of a metagraph of paths passing through a certain node. So anyway, you have some sort of a direct acyclic graph, and this graph has one source node. It can always be added, and one sink node. By which I mean that a source node is a pure parent, whereas a sink node is a pure child. It has no descendants, whereas source node has no predecessors. You can always modify your direct acyclic graph to have these sort of nodes. Okay, so and you have some weights on this graph that actually describe the transitions between over edges. Okay, so your goal is to find the path with highest score or lowest score, depending on your goal, but still these interchangeable problems, among all paths from the source to the sink. And the solution is typically given by this dynamic programming problem. Basically, you start from the beginning, and you constantly greedily optimize your current solution to get to the final optimal value, and then to get the path you backtrack. This is the idea proposed by Bellman, and actually now the next slide will be recasting this into a linear problem. So Bellman showed that that problem, dynamic programming, is equivalent to the following, gives the solution to this linear problem, which is combinatorial, because here Y is the set of all binary matrices describing paths from the source to the sink.
What is
theta? Theta is the parameter of the problem. In this instance, it's the weights on the edges of the graph. And Y is the set of all matrices, binary matrices, that represent a path from this node to this node. So basically, we have like exponential number of matrices, and Bellman's approach allows us to solve this efficiently. But more on this later. So basically, the problem is that this, if we want to use this in deep learning, this is not differentiable unless the solution is unique, and usually the solution is not unique. And the optimal solution is discontinuous. So now let's ask the question. We observe that in the linear problem we have this magic three letters, MAX, max. What is a maximum? Basically, if we have some vector, d-dimensional vector, then the maximum is basically the largest component of that vector. But we can recast it as a linear optimization problem on a unit simplex in d dimensions. So basically, if you want to take find the largest value of a vector, you take the non-negative part of the unit sphere of L1 norm and solve this problem. That's just, it can be easily shown. that this thing is equal to this one, and the optimal value of x here is argmax of this thing. So this sort of maximum is used in every optimization, and of course this thing is differentiable, but the solution is not. It's hard to take the derivative of an argmax. Although
Can you get, for example, one second, one slide back? Okay. There should be some constraints. No?
Constraints are embedded within this y, the beautiful y, the calligraphic y. So, okay, now the main contribution of the paper is that they relax the maximum. They take the following approach. They take this original problem, which had only supremum here, and they add a strongly convex regularizer, for example, negative entropy or L2, so that the problem is relaxed, but then convexity actually implies that it has many, many wonderful properties suitable for embedding within neural networks, within modules learned through gradient descent. So from convexity of this regularizer, which can be negentropy, or they consider negentropy, negative entropy, and L2 loss, the solution is unique. The solution is Lipschitz continuous, and the gradient of the whole max omega, the relaxed maximum, is equal to the solution, and you can actually compute the Hessian of this the gradient of the whole problem. Now the main question is what properties does this new maximum have as an operator, as something that you apply to vectors, to objects. First of all, you can recover regular maximum if you take just this, if you do not use any regularizer. You recover softmax, the one that is typically used in multiclass, if you use negative entropy, and you recover a so-called sparse softmax, which actually forces some components, near zero components, to be exactly zero, if you use L2 norm. Because if you have a look at this thing, if you have L2 norm here, and this is unit simplex, basically this whole problem corresponds to the projection, the optimal projection of point theta to the onto the border of the unit ball of the unit simplex.
What is D? What's the dimension of what?
Well,
of the matrix, I mean.
No, here is just like the setting is consider RD, and yes, the maximum on RD. D here is some number. It has no relation to any previous slide.
It has relation to theta, of course.
Well,
and
but
what is the dimension of theta?
It can be 2 to the power of n. It can be n. It can be 1. It can be 3. It can be.
Is it the dimension of this as a matrix?
No, not yet. Just wait a bit. So now, how do they do this transition? How do they recast the search over binary matrices into this problem? Basically, they say, okay, my search over binary matrices from from all the possible matrices is equivalent to basically trying to find the maximum over vectors from this huge dimensional space. It's huge dimensional. It's not even big dimensional. Huge dimensional. Using this maximum. Basically, if you take the original problem of finding all maxima here, this one, this you can say that you find the largest element of a vector composed of the values you take for each y. Yes, basically the calligraphic y is the number of it represents all the paths. So here's how your relaxed linear program looks like.
Do they consider cycles? Because
It's a direct acyclic graph. There are no cycles by definition. So here's how they relax the linear program, and as for dynamic problem, they use the Bellman equations, but instead of maximum here, they use this relaxed maximum. So basically, this their change. Now, the main pertinent question is, how are these two related, and do we get any profit from doing this? So they answer these questions, but the answer is not so.
Still, this optimization has a lot of parameters. No, I mean they have the number of path parameters.
This is the number of edges in your graph, actually. Bellman equation has complexity of module of the number of edges in your graph. This has complexity of 2 to the power of something, I don't know. Much more than this one. This one is just number of edges. So number of paths is exponentially more than the number of edges. So here's what they show. They show that both relaxed linear program and dynamic algorithm, this one, they are well behaved, they are convex and differentiable, their gradients are nice, and their Hessians exist. So basically, if you like SGD, you can stop here, but if you like some sort of a second order method of optimization like conjugate gradient, stuff like this, this is very interesting property that you can use.
Doesn't it have just analytical solution?
Which one? Smooth max. If you have negative entropy there, then yes, the optimal solution is for the maximum. This thing, not this thing, but yeah, max omega for this thing is log sum exp. For its derivative is this is softmax, and its Hessian is well, I can't really show it to you, but it's a simple diagonal matrix minus some low rank matrix. This one. This? Well, this unfortunately requires. Okay, so. Instead of iterating over exponential number of potential solutions, you only walk through the edges. Each time you have to solve this relaxed maximum. So the number of the number of times you have to solve this is the number of edges. If you're lucky to have an exact solution here, then all right. But if you use L2 regularizer, then unfortunately. Yes.
But from max, I think
What? Softmax? If you mean that you can actually collapse the whole formula?
Yeah.
I haven't tested it and haven't thought about it, but I don't think it is so, because you can analytically collapse and get all this like huge symbolic tree that you can compute, or you can use auto differentiation, stuff like this, to compute it iteratively, recursively. So it's not the issue here. Okay, so of course, exponential size of the number of paths versus the number of edges, which is much more tractable. So authors actually want to concentrate on dp omega. But the question is, how are they related? Unfortunately, the question is not the answer is not so satisfying. First of all, dp omega, the relaxation of Bellman equation, is convex and it can be used. Of course, that's interesting, but not that interesting as this thing. The solutions and the problems, relaxed problems of dynamic programming using Bellman equation and linear programming coincide only if you use negative entropy. For any other regularizer, you only have some sort of an approximation which depends on the number of nodes in your direct acyclic graph, and which enjoys also a nice property like this. So basically, if you reduce your regularizer to 0, you get a linear program, but nothing more. And that's their main theoretical contributions. Their practical computations amount to efficient way of computing, of backpropagating through the dynamic program to get its gradients. And they finish off with giving an algorithm for Hessian vector computation. So to be brief, computing dynamic the gradient of the optimal dynamic problem, of optimal value with respect to its parameters, is done like in any algorithm involving neural networks. You first forward pass, make a forward pass, each time accumulating the local solution at each node I, and then you backward pass using this a little bit messy formula to compute the final gradient. In fact, this is not very important for understanding right now, because in their paper they promise to implement provide an implementation PyTorch. They promised it in February, and I don't think they have implemented it yet. So we will have to wait a little bit. But still, this is like a very simple yet messy way of computing stuff. Of course, if you use auto differentiation, this can be done automatically, but it's much slower unless you code it yourself. So that's what they are trying to do right now. So. They provide also an interpretation to this, the gradient of this relaxed dynamic problem, which amounts to the gradient is equal to the average path of a random walk on this graph, but not in the forward direction of its of the graph. It's in reverse direction from the terminal node to the sink node, to the source node. And the matrix Q that was computed during forward pass actually corresponds to transition probabilities. So they also show that this holds true, and that if our regularizer is diminished constantly to zero, then gradually to zero, then the solution, the gradient of this dynamic problem, Bellman's relaxed Bellman iteration, converges to some solution from the original linear problem. This for any regularizer, but sorry. Interpretation? No. This if you use negative entropy, then some of your transition probabilities, many of them will be non-zero. But if you use L2 loss, then your support of your the number of zero elements in your transition matrix will be much higher. So that's like it sparsifies the transition matrix, the choice of the regularizer. Yes. Well, this interpretation actually tells you that it's an average path. Paths y bold y corresponds to the matrix, the binary matrix. So the average path with respect to this distribution. This holds for any regularizer, and the distribution actually depends on your regularizer. If some distributions will have non-sparse transitions, other distributions will prohibit some transitions. They actually show this in their experimental section, which I don't provide because their main contribution is this theoretical framework. So. In conclusion, they provide this theoretical framework for transforming, basically they actually prove the properties of maximum operator, of the relaxed maximum operator. They provide efficient way of computing, of backpropagating through Bellman equation for use for dynamic programming. And they they actually instantiate the exact problem settings for each of these three applications. So they provide an example for part of speech tagging. They show how you can create differentiable dynamic time warps. And they actually conduct some experiments, simple experiments, but still. And they finally give an example of structured learning, where they take attention mechanisms, where they introduce attention mechanisms to sequence problem, and for negative entropy they get like what Evgeny mentioned, transition matrix, which has a lot of which doesn't have many zeros. So basically every transition has some probability mass. But for L2 regularization, they explicitly get a matrix that that looks very that is very sparse. Basically, it contains only a couple of paths through it, which are non-zero. Other elements of the matrix are zero. So basically, this is it for this for their contribution. And if you have any questions, feel free to ask me. So.
I go back to a slide where the bounds on the performance.
Yeah, that's a pretty poor bound. It depends on the regularizer very much. If you take negative entropy, then your dynamic program will overestimate the linear program. If you take the L2 loss, then your dynamic program will underestimate it.
What is M capital?
M is some constant depending on the regularizer and the number of nodes in your graph. So it actually comes not just from this thing and the way that you use to compute Bellman equation. So yeah. So the takeaway message is if you have any optimization problem, you can try to use their smooth maximum, and with enough effort you can even plug it into a neural network and have some interesting results. For example, I haven't reviewed this paper yet. I'm planning to do a presentation on it for the next seminar or for a seminar after that, where people just said, okay, let's have a differentiable convex quadratic convex problem, differentiable layer that solves a quadratic problem which occurs in SVM, for example. So quadratic constraint problem can also be differentiable. Of course, there are some peculiarities, assumptions, but they say, well, in the general configuration, there are no non-differentiability issues.
But there are also the assignment problems, such that you have like K1 objects on the left,
yes.
K2 objects on the right, so it's also neural networks are used to do that.
So assignment, you mean like the marriage problem?
Something like that, yeah. So it's used in object tracking, for example. When you have consecutive frames, you detect objects and you have to somehow identify that as the same object in the various frames.
Yeah, one of the messages in the paper was that sometimes those handcrafted costs of assigning objects are not optimal, and basically you can use this layer atop of the proposed tracking device that can actually learn more task-dependent and optimal costs for alignment. So that's what their practical contribution amounts to. Okay, so I guess this concludes the today's seminar.
Yep, well, thanks, Ivan.